So thanks very much for the introduction. My name is Mraz, and together with my colleagues from ETH Zurich and Google, we will present to you today our work on Pecan, which is our new system for cost-efficient machine learning data preprocessing with automatic transformation ordering and hybrid placement. So let me begin by describing the essence of online data preprocessing in machine learning workloads. So typically, you will start by having your data in records that are stored on disk or potentially in a cloud bucket such as S3. Then you will have your input pipeline, which fundamentally performs three tasks: extraction, transform, and loading. And this typically takes place on a CPU, which is in contrast to the model training itself, which typically takes place on an accelerator such as a TPU. And today we want to focus on this first part, the input pipeline, and to delve a bit deeper into what actually happens inside of it. Here is an example where we take the data from file, then we extract the image of a cat, for example, perform some transformations, and finally we're ready to load our data into the model. Now the issue is if we collocate these two fundamental tasks of the input pipeline and the model training on the same machine, is that we typically don't have the right ratio of CPU and memory resources to the accelerator resources. And this can, of course, be very wasteful, which is not good for large-scale machine learning. So why do we want to focus on this first part? Well, what we see in recent machine learning workloads is that this increasingly becomes the bottleneck of the overall system. So as machine learning practitioners are adding extra data augmentations to obtain a very strong model, this whole process takes up a lot more compute power. And it's important to note that we cannot perform the input pipeline beforehand, because then we would have the same data sample produced in every epoch, and we wouldn't get a robust model. So therefore, we have to optimize this in an online setting. And a common solution to this is to actually disaggregate these two fundamental tasks. So here you have on the bottom your storage layer, and then in a well-known controller worker architecture, you can essentially infinitely scale the input pipeline's resources. And you do this by adding, keep adding extra workers that will perform this input pipeline. And on top, we still have our training clients, which are typically our TPU or GPU nodes. And these are fed with data from our disaggregated workers. As you can see, it's not an easy task to coordinate all of these features. So how does disaggregated preprocessing help us in terms of cost? Well, what we see here is our 5 machine learning workloads. ResNet, SimCLR, and RetinaNet are computer vision models, and ASR Transformer is a speech recognition model. And finally, we also include ResNet run on a more powerful TPU. This is to show how our policies can benefit across different hardware architectures. Now, on the left-hand side, we see the traditional setting where you have a collocated setup, and this corresponds to the blue bars you see in the graph. And since we have everything sat on our TPU node, we only have this full bar. Whereas moving on to the disaggregated setup, which are the orange bars, here the cost of the machine learning workload can be fundamentally split between the solid TPU cost, and then on top of it, we have the hashed cost for the remote workers, which needs to be added together. Now, as you can see, disaggregating allows us to reduce the cost significantly across these workloads, and it does so by scaling out these remote workers and therefore reducing the epoch time. However, this doesn't come for free, and as you can see in some of these workloads, more than half of the cost is still coming from the remote workers. So today we want to have a look at how we could reduce this portion of the cost further. And we want to do this while keeping the training time at its minimum. So what are our key contributions in our paper today? Well, first of all, we asked ourselves, how could we minimize the need for these remote resources in the first place? And if we minimize the number of remote resources, then we will directly also minimize the end-to-end cost. And for this, we developed an auto placement policy. And acting orthogonally to this auto placement policy, we also had a look into deeper into the logic of the preprocessing pipeline itself. And we had a look at whether we could somehow redesign the input pipeline to improve throughput. And thanks to our auto order policy, we've actually managed to achieve just that. So how exactly can we reduce the number of remote workers? Well, what we see in a disaggregated setup is that we can minimize the epoch time. However, we still have, on our training client, we still have a lot of CPU resources which will then be underutilized. So we're trying to see if we could find a balance between using both remote and local resources in order to make the most use of this sunk cost that we've already paid for. Now, you might think, well, this is a pretty simple task. We just add a single worker process on the training client. But in fact, there are multiple aspects that make this a difficult task. And most importantly, these CPUs located on the training clients, they cannot just solely focus on data preprocessing, but rather they also have to do several auxiliary tasks. For example, they have to have some CPU cycles to collect data samples that are generated from the remote workers, and they also need to be able to load preprocessed data from the CPU memory into the TPU memory. So this is not an easy task to figure out the right configuration of how many of these workers can we move onto the training client. And secondly, as we all know in systems, getting the right parallelism is always a difficult task. And this is something that we see is difficult to get right up front. So to demonstrate how difficult this task truly is, what we have here is a grid search over the number of remote workers on the y-axis and the number of local workers on the x-axis. And on the left-hand side, we measured the time per epoch under each of these configurations, and then using this time, we calculated what the cost would be. And if you look at the numbers, an ideal setup in this case would be to use 6 remote workers and 9 local workers. But this is something that is very hard for an ML practitioner to guess. As you can see, the search space is very nonlinear, and it will vary depending on the hardware ratios that you have. So since this is such a complex space, and using an analytical approach would not yield a very good result here. Instead, we want to use a policy that would achieve this instead. So let me move on to an example of how our auto placement policy achieves this. Well, we begin by using a single remote worker. As you go down the y-axis, we increase the number of remote workers, and on the x-axis, we increase the number of local workers. So we start by a single remote worker, and then we scale out up to 5 remote workers. And we do this because we know that with remote workers, we can scale essentially infinitely, and we can remove the input pipeline bottleneck without a problem. And we do this also because adding and removing remote workers is very cheap. So we first want to focus on our main goal, which is to keep our TPU occupied. So now that we've reached the point where our TPU is as busy as it possibly can, now we try to reduce using these remote workers by adding local ones instead. And we continue adding local workers until we see a performance decrease. And this means that we don't have enough cycles left for these auxiliary tasks that I mentioned previously, and therefore we have to stop adding local workers. So now that we have these 3 remote workers, what we can do is we can remove some of the remote workers because we now have this extra workforce that can take over their jobs. And iteratively, we remove remote workers and add local ones until we converge to an optimum. So in this case, we ended up using 2 remote workers, which is much better than the previous version, which would use 5 remote workers. And as you can see, the trade-off is nonlinear because we've traded off 3 remote workers for 6 local ones. So how does this translate into end-to-end cost savings? Well, in this graph, we see once again the collocated and disaggregated setup we saw previously. And on top of that, we now also have fast flow, which is another system which tries to alleviate input pipeline bottlenecks with low cost. And finally, in green, we have our auto placement policy. And as you can see, across all these 5 workloads, we successfully reduce the end-to-end cost. By the way, if you check the proportion of the solid bar of the TPU cost, this will directly represent also the end-to-end training time. So the lower the TPU cost, the lower the training time. Now, orthogonally to our auto placement policy, we have another strategy that can help reduce end-to-end costs, and that is by using transformation-aware data preprocessing. So until now, typically, machine learning frameworks such as TensorFlow or PyTorch would treat the input pipeline fixed as it's written by the programmer, and it wouldn't change the internal logic. But what we see as a very nice property of machine learning workloads is that their point is to add randomness to the data. And rather than producing a specific example, we want to add this randomness, random perturbations, but their order is not critical because we just want this diverse data set. So what you see here is 2 versions of an input pipeline which uses the crop and flip transformation. On the left-hand side, we begin by cropping the image and then flipping it, whereas on the right-hand side, we crop it at the end. Now, what difference does this make? Well, on the left-hand side, we're flipping a much smaller image, so much less pixels need to be flipped, which is much cheaper in terms of CPU cycles. And therefore, we can achieve higher throughput. Now, it is important to note that the end image is not the same here. But what we are asking ourselves in this work is, could we use some more aggressive reordering to increase throughput without impacting accuracy? And as I will show you in a moment, thanks to these favorable machine learning pipeline properties, this is possible. So let's move on to an example of how the auto order policy would execute. So first of all, it can use the types, ranks, sizes, and instance counts to determine the volume of the data flowing into the transformation and flowing out of it. And we can calculate then a new metric which we call the inflation factor, and that will determine whether the transformation increases or decreases the volume of the data. Now, in the previous example, this was a very easy task because you only have 2 transformations and it's pretty obvious what their status is. But in practice, you might have a lot of transformations where the inflationary status depends on what exactly was the input. It might also be randomly dependent on a random number generator, or you might also have certain filtering operations which filter out differently depending on other factors. So now moving on to the example, here we have 5 transformations in a pipeline, and the auto order policy begins by classifying these transformations by their inflation factor. So the ones in blue have an inflation factor of less than 1 and will decrease the volume of the data. The red ones will increase it, and finally T5, it does not change the volume of the data. So now the auto order policy suggests a new order where we've moved T3 forwards, and And instead, we've moved T2 and T4 towards the end. And now you can see that T5 is computed on a much smaller volume size, which is much more computationally efficient. Now, just to note, our system does also support barriers. So if you as a user say that, for example, T3 must stay on its current position, you can set this as a hint, and our policy will respect this barrier and only reorder ops within a subsection of your pipeline. So how does this translate into cost savings? Well, as you can see, for at least 3 workloads, we can drastically reduce the end-to-end training costs in ResNet, SimCLR, and also ResNet on a more powerful TPU. As you can see on RetinaNet, on the other hand, the cost remains the same. And the reason for this is that the original input pipeline was already very efficient. So our auto order policy correctly identifies this and does not make significant changes to it, and we still keep our optimal pipeline design. So as I mentioned earlier, we don't always get the exact same value as before. So it's important to have a look at what impact our auto order policy has on the end-to-end accuracy. And what we see is that actually the impact is very negligible. In fact, for our 3 vision models, the delta is less than 0.4%. Then for ASR transformer, this is slightly larger, but you have to note that here the standard deviation is a lot higher than in the previous ones. So we can still safely conclude that the auto order policy only impacts model quality in a marginal way. Now, I've shown you these 2 policies, so how do they come together? Well, in this diagram of our system, we have our storage and our remote and local workers. And now on top of this, note in the orange box, we have our auto order policy, and we execute this before the job training begins. And the reason for this is we can use these statically inferable values, and we can optimize the throughput directly from step 1. So we want to do this as soon as possible. On the other hand, the auto placement policy is something that we cannot easily execute in an analytical way. Therefore, we need to wait for runtime metrics. And this is something that the dispatcher will do for us, and then it will suggest in which direction we should increase or decrease certain workers. So what's the impact of these policies put together? Well, now on top of our previous bars, we also have the brown bars, which is putting Pecan's policies together. And as you can see, we've actually reached the minimum cost across all 5 workloads. And for several of these, we've actually managed to remove the need for any remote workers at all. So we're just left with the TPU cost, which is essentially the best we can hope for, assuming that the TPU stays the same. So to summarize the key takeaways here, we've managed to remove the input pipeline bottleneck, reduce the training times and costs, and now we set a new state of the art. And compared to a disaggregated system, we can reduce the preprocessing costs by up to 97%, and the total cost by 34%. So let me conclude by reiterating the most important points. A disaggregated preprocessing setup removes the input pipeline bottlenecks, but we still have this non-negligible cost of the remote workers. And this is something that we need to optimize. And for this, Pecan presents 2 policies, each of which they collaboratively help reduce the end-to-end cost. First, we have our auto placement policy, which exploits the local resources to mitigate the need for remote ones. And then we have our auto order policy, which makes use of these favorable machine learning pipeline properties to move towards transformation-aware preprocessing. And as we can see from the results, our system sets a new state of the art, and compared to a disaggregated setup that researchers have been using in recent times. We can reduce the remote resources by 87% on average for preprocessing, and 34% in the total cost. So thank you very much for your attention, and I'd be happy to answer any questions.